to y continuous. Nothing. Is F necessarily a contraction? Contraction nothing. Is F necessarily a non-expansive? Nothing. Here we need to only give an example. Our example is also the hyperbola. So let x equal to 0 to infinity, which is also equal to y, where both x1 and y is equal, and f from x to y is given by f x equals 1 over x. Simple example. And then you take 2 points, x equal to x1 equal to 3, x equal to 4. Then the x1 minus x2, x2 minus x1 is 1. F x2 minus f1, x1 is equal to 1 over 12. Oh, I got it. Oh, I'm right. Is that right? No. This is your f.
Yes.
This is f x1, f x2. So you're taking. This is now 1, that is 1 over 12.
Yes.
So you don't have a coefficient, the Lipschitz coefficient. At most 1, so that the Lipschitz inequality is absolute value of the function difference cannot be bounded by the absolute value of the distance between the 2 points using the constant k, which is most one. So this gives a continuous mapping which is continuous. I proved it in the first year calculus. And continuous mapping which is neither contraction mapping nor non-expansive mapping. Now 9 is the Gardner information which we have talked about. Gardner question, and this is not going to be examined. Of course, the keyword we typed and then I got 1. Some very shallow answers. Number 10. Question number 10 was originally question number 1 in the lecture notes. In the lecture notes, I have prepared it until the end. But I was advised not to hand it to you in the beginning, which I was intending to do. Which is probably based on some assumption about you, whether you might attend the lectures and write the exam and so on. But I don't really know whether those assumptions are true or not. But I did follow the instructions. So this was question number 1, which asked you to verify the 3 distance functions we defined for Euclidean spaces satisfy the 3 metric axioms. I am sure you have done this in some of your courses already, but have you done? If you have done, let me know. Even if you have done already in functional analysis, I'm going to still write it because I think my writing will be perfect. There's no flaw in it. This is what I'm always trying to. Everybody listens to me and says that this guy is always praising himself. Nobody else praises him, but it doesn't matter because this is definitely perfect, no problem. So the three Euclidean distance. Number 1 is Euclidean distance, which is rho 2 of xy x, y are vectors in Rn. So we use the subscript to denote, under the letter to denote the component. This is given by square root of x1 minus y1 squared, x2 minus y2 squared, all into xn minus yn squared, x squared. And American people call it Manhattan distance. I don't believe it. It does nothing to do with Manhattan. Manhattan streets are not rectangular. I was there many times. Some of them are triangular, very nice. For example, what is called Times Square. People who haven't been in New York, they think Times Square is some square like Jahangir Garden or something very nice. It is not. It's a very sharp triangular area with few roads converging there, and that is Times Square because Times magazine office is there. And the people call it square. I don't believe it. It's a United States. Manhattan distance doesn't show anything. It's just a very silly word. But it's in our writing it gives us some of the component, absolute values of the component differences. You are all familiar with these things, should be. In the linear algebra, also this was mentioned somewhere in the metric space part. This is the L1 distance, ρ1 distance. And then you have a rho infinity or zero distance. Let me write now, instead of writing infinity there, write zero. This is maximum of these individual terms. From this set of n numbers, we are taking the largest one, if there is the largest one. What do you mean if there is the largest one? There is no, this is a finitely many fixed real numbers. Therefore, there must be at least one largest one. What I say there is the largest one means that we are taking one of them if the largest one is many. We're not saying that, we're not implying that there is no largest one in some cases. No, that we're not implying. So we want to prove that these satisfy the three axioms. So let us consider that one first. The three metric axioms are: number one is distance is non-negative, and it is distance is zero if and only if you're going from the same point to zero. And that is fine because we know that each of these is non-negative because xi, yi are real numbers. Therefore, xi minus yi squared is non-negative. If it is not from there, we are not sure. Therefore, these terms are all non-negative. Therefore, if you add them up, you have a non-negative number squared. This is arithmetic square root, which is non-negative. This implies that rho 2xy is non-negative. And rho 2xy is 0 if and only every one of these becomes 0.
Yes.
Which means that for each I,
xi equal to y.
xi equal to yi. This is the definition of two vectors equal. In vector space. So the first axiom is verified. Second axiom is equally easy because this is equal to therefore the with some words which is there, rho 2yx is equal to rho 2xy. But you need to really write this down. very good exam paper which you can get lots of marks. Basic, and nobody would complain. Right? This, you will all be 100% sure you can do this, right?
Yes.
So you see, this is given, such a question is given 10 marks. You already got 10 marks already. So you should really be sure about these things. So this is true. The second axiom is satisfied. Second condition is satisfied. This is first condition is satisfied. Now, this is the other one. What people call it in vulgar words, triangle inequality.
Yes, sir.
How do you do that? For triangle inequality, let me tease the applied mathematician, because they are applied mathematicians. Oh, he's gone. Applied mathematicians will quickly pull out Cauchy-Schwarz inequality, and it follows from that and on. But Cauchy-Schwarz inequality must be proved first. If we are doing mathematics, we cannot do this at all. Einstein proved it, therefore we believe it. No. There is no such thing. So we need to go more further to the base. We look at the sum of two vectors. Its length squared. And we are now making reference to the, because this is Euclidean space, we will make reference to the inner product. So this is given by inner product of this vector with itself. This is how we prove this in linear algebra, right? This is equal to inner product of xx. No, let us use uv here because we're going to do some substitution afterwards. I can't see the
This one.
uv are vectors. uu plus uv plus vu plus vv. This is standard in linear algebra. And this is at most, because that one is not greater than the square of the length of u.
This is juice.
Plus 2uv. We know that this in Euclidean space, the inner product is symmetric.
Yes, sir.
Here we are using it. So this is a 2 of uv, which is smaller than this, and smaller than equal to this, and then plus v length squared. And this is can be written as length of u plus length of v
Whole
squared.
And
Now, if you take the square root, then you have
when we write inner product of u with itself, this is actually the norm. So why we write greater than? When we take inner product of u with itself,
yes.
this is actually the norm.
This is the norm. Yes.
So why we write greater than
Greater than
on the right hand side?
this one. This one.
Yeah.
It is this is not greater than that one.
These are the same thing.
No. Wait a minute. Inner product can be even negative, isn't it? This one is always non-negative.
Yes.
Inner product is negative when we have different vectors. When the vectors are same, then always
Yes, you're right. So here this inequality is not there.
there should be equality.
This is the equality. Thank you for this. This is an equality, and that is also an inequality. Then how do we get there's something here. Oh, these two terms. This one is this is not greater than this.
Yes, sir.
Yeah.
You're right. So this is an inequality here. It's this one. Sorry. Thank you for the clarification. So these two are no problem, but only gives the inequality. Now what we are, okay. Now let us substitute in this inequality after taking square root u equal to y minus x. It's again elementary substitution. U equal to y minus z. Oh, u equal to y minus x. V equal to z minus y. And this implies that u plus v is z minus x. Substitution, and after that we get z minus x is at most y minus x plus z minus y. And this is your Euclidean, this is rho 2 xz. This is rho 2 xy. This is rho 2 yz. So the third condition is satisfied.
I have a question.
Yes.
These properties which are in the inner product space, especially by using inner product property.
Yes.
So it might be possible that there exist some numbers in the bigger space, that is the metric space, which does not satisfy this inequality. So we should move towards the Cauchy-Schwarz inequality.
In some other spaces, you're saying that
in the metric space, there might be exist some numbers which does not satisfy this inequality.
no, in Euclidean space, this is definitely satisfied, as you have just proved. We are talking about R in Euclidean spaces. This, because if you have X and not a metric space, which could fail any one of the three conditions, in which case the third condition can be failed. There are lots of sets which are not necessarily metric spaces. Of course, for any set, you can actually introduce metrics and make it a metric space, no problem. For example, discrete metric.
Yeah.
And we're going to prove it next. This is only one part. The other part we will also do. So this says that Euclidean distant function satisfies all three conditions for Euclidean space of any dimension to be a metric space. I think your question is probably a different one because I didn't quite understand your question.
I just say that we prove this inequality in the inner product space.
Yes.
So it might be possible that there exist some numbers in the bigger space, that is in the metric space, which does not satisfy this inequality.
Of course, there's some other spaces there is no inner product. Geometric spaces has inner products, but some of the, for example, the Minkowski space, the physicist space, has one of the quadratic, in the quadratic form, one of the term is -1, the coefficient.
But we are discussing the metric space, that is rho 2 space.
No, in this case we're discussing Rn, this space, not the metric space, Euclidean. Euclidean space Rn, we have three distant functions defined in the lecture. And we're going to carefully verify that they all satisfy the three conditions. We didn't do that in the lecture. For any Euclidean space, we define at least three. There are much more, many other things. But these three we're going to verify.
Okay.
And what I'm doing here is probably not, how to say, it's not a research. If you are only interested in research, this is no external or internal examiner will complain. I can give this the first question, which carries 12 marks, for example. If you know all the details of this, then you will 100%, you know it before I write it on the board. But if you do know this, all of this, then you will pass this question at least. That's what I'm trying to suggest. It is not an unknown thing, anything research or something We are doing each old things. So, but this is very good for getting some marks. You see, mark is, if you are going to see exam, you have to have some passing mark at least. And then after that, you might distinguish people who are clever. And we are not going to, of course, you are all clever because you are at least MPhil student in Pakistan. But we cannot really assume that you are clever and we want to give you all new questions. That will be failing lots of people, which is not which is, in my opinion, it's an evil thing to do. I don't want to do evil things. So we will guarantee some bottom line by 26. Because I didn't plan this course to be examined before I came. But examining is a good idea, but I agreed, so we need to rescue this. We haven't done any of the research yet. After 1st of December, if we can still do it in 1.5 weeks' time, we will probably do at least one paper. We're not writing paper, we will introduce the result proof, complete proof of one paper, results of one paper. And which may or may not be our paper. Our paper is in the batch 9. Batch 8 is 1976, published in 2000, which is not done yet.
So time is up.
Huh?
Time is over.
Innocent classes are saying time is over.
Time is up. Okay, so we cannot even do the row 1. We will try to add some lectures even in the evening after 1st of December. If you're not all tired by this 2 weeks of workshop, and I think this workshop is going to be very tiring, you have to understand that.
Yeah.
And then after that you have a conference.
Yeah.
This thing, it's working, right?
Sir, question number 10 is mandatory for exam point of view.
Yeah, question number 10 is, I can guarantee that I can give it as an exam question. Which means if you, this is well known to you already.
Sir, I think two question